also probably include two points more in test number 3 as a bonus here. So I will help you as much as I can, girls. But please, you need to help yourself also. Yeah? You need to work a little bit harder. Okay, no problem, girls. All right, so let's talk a little bit about coordinates in general. So before I talk about spherical coordinates, I want to summarize a little bit what we know about coordinates. When we work in R2 in 2 dimensions, you of course have the rectangular coordinates. Rectangular. What are the rectangular coordinates in R2? Do you know? X and Y. Thank you. Yes. X and Y, no problem. You have your R2, the space, the plane R2. X is here, Y is here. So any point will be given by its X coordinate and its Y coordinate. These are called the rectangular coordinates. But in R2, we also have what we call, what are the other coordinates we know in R2? Girls, do you remember? The polar ones. Yes, thank you, Salha. So we have the polar coordinates, which are R and theta, yeah? Okay, so in this case, you have a point in the plane, then R is this distance and theta is this angle. So the point P can be given by these polar coordinates R and theta. And of course, these two sets of coordinates are related. X will always be R cosine theta and Y will always be R sine theta. Yeah, this is the connection between the rectangular coordinates and the polar coordinates. Well, in space, in 3 dimensions, the rectangular coordinates, what are they? X, Y, Z. Thank you, Noria. So rectangular coordinates are X, Y, and Z. Now, last class, we talked about another set of coordinates in R3. Do you remember what we called them? Last class, not spherical. Spherical is today's class. Today's class, we'll talk about spherical. But last time, the cylindrical, yes, cylindrical coordinates. Cylindrical coordinates, which are R, theta, and Z. So basically, we replace 2 of these coordinates by the polar coordinates R and theta, and we keep the third one exactly as it is, like this. So that is basically the way the cylindrical coordinates work. Okay, and the thing we mentioned regarding this was when you work with polar coordinates, dA, yeah, so in R2, when you want to integrate, the dA, which is dx dy, is equal to R. Do you remember what we have here? R dr d theta. Thank you. Yes, like this. So we have this, and in R3, the dv, which is dx dy dz, is when you work with cylindrical coordinates, it's r dz dr d theta. So that we need to use this to integrate. So we use these two rules to integrate either in polar coordinates or in cylindrical coordinates. So we use this for integration. So today we will add another set of coordinates. In R3, we will add what we call the spherical coordinates, and that's it. Spherical coordinates. Today's class, I will introduce you to this idea of spherical coordinates. So let's see what they are and how we work with them. Okay, spherical coordinates are these. So imagine you have a point P in the space with rectangular coordinates x, y, z. Now, take the projection into the xy plane of this point P. Yeah, project it into the plane, and then the angle theta will be this one. So it's the angle theta is from the positive x-axis to this vector OR. Phi is here, is the angle between the positive z-axis and the vector OP. So this angle phi, like this. And finally, rho is the distance OP, basically, from the origin to the point P. That is called rho. So basically, here are the important definitions. So rho, yeah, will always be equal to the square root of x squared plus y squared plus z squared. Very important. Phi is the angle from the positive z-axis to the vector OP. Theta is the angle from the positive x-axis to the vector OR. And basically rho is always positive. And phi, yeah, you can see the angle phi. Imagine you take a point anywhere here. Phi is this angle. So if P, for example, imagine P is on the z-axis. Imagine that the point P is on the z-axis. What will be the value of phi in that case? 0. Thank you. Yes. Imagine P was on the plane xy. Your point P is here. What will be the value of phi this time? 90 degrees, 90, exactly 90 degrees, like pi over 2, yeah? You can see from the z-axis to the plane xy, that angle will be 90 degrees. Imagine you take a point below xy plane, down here. Then the angle phi will be a bit more than, yeah? Okay, what is the maximum value for phi? The maximum value for phi will be 180 degrees. Exactly. So you can see, yeah, phi is always from 0 to pi. Not possible to have phi more than 180 degrees. Not possible. Yeah. Just imagine wherever you put the point P, phi will be somewhere from 0 to 180 degrees. How about theta? What can you say about the angle theta? If, for example, if I take the point P on the x-axis, suppose, imagine you have the point P here, what will be theta in this case? 0, yes? Yeah. Suppose P is on the y-axis. 90 degrees, very good, 90 degrees. Yeah, 90. Suppose you have the point P this time on the negative x-axis, on the other side. So what will be theta? 180, exactly. Now, suppose you have the point P on the negative y-axis, 270, exactly. And then when you come back, so theta is always from 0 to 360 degrees, which is basically 2 pi. So theta could be anywhere from 0 to 2 pi, like this, like that. Okay, and then we have using a little bit of geometry and trigonometry and so on, we have these relations. X is rho sine phi cosine theta. Y is rho sine phi sine theta. And Z is rho cosine phi, like this. So we have these three connections between the rectangular coordinates x, y, z and the spherical coordinates rho, phi, and theta. By the way, here, phi comes first and then theta after that. So rho, phi, and theta. Okay, now here is a point P given by its spherical coordinates. That means rho is what? 8, yeah? Good. Phi is, so it's always rho, pi, 45 degrees, so pi over 4. And theta is pi over 3, which is 60 degrees, yeah? So like this. Now the question is, find the rectangular coordinates. That means what is x, what is y, and what is z. Okay, that is what we want. Okay, let's use the rule. Yeah, what is x? X is rho, which is 8. So I'm going to use the rules. So it's going to be 8 sine y. What? Yeah, sine phi, which is pi over 4. Yeah. And then cosine theta, which is pi over 3. And if you take your calculator, yeah, if you take your calculator, you will see 2 square root of 2 or 2.8. Yes, 2.8 is fine, but exactly 2 square root of 2. That is the x. Yeah. So the value of x, yeah, here is 2 square root of 2. Now I want to find the y. It's still 8 sine pi over 4. Notice that the beginnings are the same. Yeah. But x has a cosine and y has a sign, pi over 3. Okay? So like that. And then you take the calculator again, and you will see 2 square root of 6. Yeah, 2 square root of 6 is this number. And finally, the z here, z will be basically rho 8 and cosine phi, so pi over 4, and it's going to be 4 square root of 2 as the z coordinate of this point. Are we okay with this? Yeah. So here are the spherical coordinates. And these are the rectangular coordinates. So notice then what you have in the spherical coordinates. You have a rho and two angles. First, the angle with the z-axis, with the positive z-axis, and then the angle with the positive x-axis. So that is, these are called the spherical coordinates. Okay, so let's move on a little bit. Okay. Rewrite this equation of the cone. This is a cone. It's graphed here, or at least half of it is graphed here. And we want to rewrite this. Yeah, we want to rewrite this using spherical coordinates. Okay, all right, Shama. What you wrote there is using the cylindrical coordinates. What you wrote is perfect for cylindrical coordinates. Now we're going to use the spherical ones. Remember, in the spherical coordinates, yeah, z, yeah, is rho cosine phi. So we substitute. So that means z squared will be rho squared cosine squared phi. So let me leave it there for the moment. Yeah. And then the x squared plus y squared. I'm going to deal with this now. So one side is this, the other side is this. Now, x, remember, is rho, okay, sine phi cosine theta. And I square that. So put square, 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 plus the y squared, rho squared, sine squared phi times sine squared theta. Yeah, times sine squared theta. Now let me simplify this a little bit. I'm going to put this as a common factor. So it's going to be rho squared sine squared phi, and then I open a bracket. What will be inside the bracket? Anyone? What will be inside the bracket? Yeah, it's going to be 1. Why is it 1, Noor? Why is it 1? Yeah, it's basically, thank you. Yeah, cosine squared plus sine squared. It's this term and this term will be inside the bracket. And of course, this is equal to 1. So the whole expression here is rho squared sine squared phi. Now, I'm going to, so that means this is equal to this. Yeah. So rho squared cosine squared phi is equal to rho squared sine squared phi. So that's basically what the equation is. And then we can simplify rho squared and rho squared will cancel. Yeah. So you will get cosine squared phi equal to sine squared phi. So that means we now, when you have something like this, there are two possibilities. Either cosine phi is the same as sine phi, which means okay, well, that means tangent phi is equal to 1. Yeah, which means pi over 4, exactly. So from here, I can say divide both sides by cosine. So you will get tangent phi is 1. So phi will be tan minus 1 of 1, which will give you pi over 4. So basically, we are getting the first possibility is phi equal pi over 4, which is actually this cone here. Every point on the cone has a phi equal to pi over 4. And then the other possibility is, what is the other possibility? When you have a square, yeah, minus, yeah. So cosine phi is minus sine phi. This means in this case that tangent is minus 1. Yeah. This means tangent of phi is minus 1. So phi will be tan minus 1 of minus 1. And this will give us 3 pi over 4. So phi is 3 pi over 4, which is basically the other possibility. You can see now 3 pi over 4 is this angle. Every point on this cone has a phi equal to 3 pi over 4. So that is the second part of. So basically, therefore, this equation, z squared equal to x squared plus y squared, when we change it to spherical coordinates, so you start with this equation. If you want to rewrite it in spherical coordinate, it becomes two equations. Either phi is pi over 4 or phi equal to 3 pi over 4. So these are the two equations that we get from the initial equation that we started with. Are we okay here? Yeah. So what we did was we replaced z with this. Yeah. So z is equal to that. So z squared will be this. And x squared plus y squared, I do all of this work, so I get this. So now that means this is equal to that. And then we just simplify and see what happens with those equations. Okay. Now, here, the equation of a sphere of radius k centered at the origin. You may remember that in rectangular coordinates, the equation of a sphere is x squared plus y squared plus z squared equal to the radius squared. Yeah, this is the equation of a sphere of radius k centered at the origin. Now, if I want to change this into spherical coordinates, now you need to remember that rho is the square root of x squared plus y squared plus z squared. This formula is important. So that means also that rho squared x squared plus y squared plus z squared. So what you have here is really rho squared equal to k squared, like this. And because rho is positive, then there is only one possibility here. So rho is equal to k. So that is the equation of a sphere of the sphere in spherical coordinates. Like this. Okay. Yeah, basically, if you take a point on the sphere, then rho, yeah, and you assume that the radius is k, rho is always going to be k. And that is the equation of a sphere of radius k. So rho equal to k. Okay. So, for example, if I give you this sphere here, I give you this sphere. Yeah, 2, 2, yeah, like this. What is its equation in spherical coordinates? Equation in spherical coordinates. And equation in rectangular coordinates. Rectangular coordinates. First, what is its equation in rectangular coordinates, x, y, z? If you have a sphere of radius 2 centered at the origin, what will be its equation in rectangular coordinates? X squared plus y squared plus z squared equal to, yeah, 4. That's it. That's the equation of the sphere in rectangular coordinates. You should know this now. Okay? That is the equation of a sphere of radius 2 centered at the origin in rectangular coordinates. Now, this equation, if I want to write it in spherical coordinates, then it becomes, yeah, remember, this side will give you rho squared equal to 4. So that means rho is 2. That's it. Yeah, that's all. Yeah. Okay? So remember this. The equation of a sphere in rectangular coordinates, it's this. In spherical coordinates, it's this. In general, of course, if the radius, yeah, in general, rectangular coordinates xy plus y squared plus this is r squared. And in polar coordinates, sorry, in spherical, it will be rho equal to r, like this. Yeah. All right. So this is what we are saying here. Yeah. This is the equation of a sphere in spherical coordinates. Now, if you take an equation theta equal k, for example, theta equal to, let's say, pi over 3, like this, then what you get is a plane. Yeah. All these points have a theta equal to this angle that we are choosing. So theta equal k describes a vertical plane with its edge along the x-axis. So the equation of this plane is theta equal to k. Phi equal k, we have already seen this. Phi equal k is a cone. If the angle, if k is up to 90 degrees, the cone will be up like this. If k is bigger than 90 degrees, then it's going to go down like this. So equation of this cone, yeah, phi equal to this angle k, yeah, like this. Okay. Phi equal pi over 2 is exactly all the points on the xy plane. Yeah. All the points on the xy plane. Yeah. If you take a point here, then the angle phi is exactly 90 degrees. So any point on the xy plane has a phi equal to 90 degrees or pi over 2. Okay, let me just do okay. Now, of course, we use these spherical um, coordinates to find integrals. So I will do one or two examples and then I will stop today. So when we use spherical coordinates to integrate, dv is given by this rule here. dv is rho squared multiplied by sine phi, and then d rho d phi d theta. It's important to remember this. It will allow us to find triple integrals. Okay, first, I'm going to use that. So here is a question. So I want to find the volume of a sphere of radius r, say. Yeah, r could be 3, 4, 5, doesn't matter. So I want to use these spherical coordinates to find the volume. By the way, do you remember the formula for the volume of a sphere of radius r? Anyone remembers what the volume of a sphere is? If I give you a sphere of radius 2, 3, 4, what is the volume of that sphere? Do you know the rule? For, no, okay. For example, the area of a circle of radius r. Do you know what the area of a circle of radius r is? Anyone remembers? Yeah, pi r squared. Good. Pi r squared. Good. Well, there is a similar rule for a sphere. If you take a sphere of radius r and you want to find its volume, no one remembers this? Okay. Yes. Okay. No. Thank you. So it's 4/3 pi r to the power of 3. Yeah. This is the volume of a sphere of radius r. Now what we are going to do is I'm going to prove this. I'm going to show you why is the volume equal to 4/3 pi r squared. We can do that using these spherical coordinates. Okay. For the area also we can use polar coordinates. So let's find the volume of a sphere of radius r using calculus. So the volume will be the triple integral over the sphere of dv. So that's the general formula. Now, imagine you take a sphere, yeah, like this, of radius r, yeah, and you take the point P inside. So in this sphere, what can you say about phi? Yeah, phi goes from where to where? If you are moving in this sphere, what are the boundaries for the angle phi? 0 to pi. Yes, 0 to pi. All the way to more than 90 degrees. You can go down here. Yeah, you are still in the sphere. So phi will go from 0 to pi. Yes. How about theta? 0 to 2 pi. Thank you. Yeah, 0 to 2 pi. And finally, rho is this distance from 0 to, if you are inside the sphere, what is the maximum value? Yeah, sphere of radius r. Huh? So small r. This r can be 2, 3, 4, doesn't matter. Okay, so therefore, I can say now I can move into spherical coordinates. So dv, remember, is rho squared sine phi. Yeah, d rho, d phi, and d theta, like this. Now, rho from 0 to r, phi from 0 to pi, and theta from 0 to 2 pi. So now I need to calculate this integral, and I should find 4/3 pi r to the power of 3. Okay, now the way we're going to do that is 0 to pi and then 0 pi. Now let's integrate with respect to rho. Yeah. So sine phi is a constant. What is the, yeah, it's going to be rho power 3 over 3. Good. From 0 to r. And then d phi d theta. Okay, great. Now, let's integrate 0 to 2 pi, 0 to pi, sine phi, yeah, and then substitute. And if you substitute, you will get r to the power of 3 over 3. Yeah, good. And d phi d theta. Okay, now this is a constant. I can take it out of the integral. It's not a function of phi or theta, so it's a constant. 0 to 2 pi. And then I integrate sine phi. What is the integral of sine phi? Minus cosine. Good. Thank you. Phi. From phi equals 0 to pi. And the d theta, I will keep it here. So r3 over 3, integral from 0 to 2 pi. Substitute. Yeah, it's going to give you minus, yeah, minus 1, minus 1, and minus another, okay, minus 1 also. Cosine 0, yeah, like this. D theta. So the whole thing will be 2, yes. All of this will be 2. So 2 r cubed over 3 integral from 0 to 2 pi d theta. So 2 r3 over 3 integral of d theta is theta from 0 to 2 pi. So 2 r3 over 3 multiplied by 2 pi, and we are getting the formula 4 over 3 pi r to the power of 3, which is the volume of the sphere. Of radius r. Okay, great. So that is actually where the formula comes from. 4 over 3 pi r cubed. You can, yeah, you can prove it using calculus. It's a really powerful tool. Yeah, calculus can allow you to get so many things. Even the area of a circle, by the way, the area of a circle, pi r squared, you can use it, you can get it by using polar coordinates. You can get the pi r squared using polar coordinates very easily. So that is how we prove that the volume of a sphere is 4 over 3 pi r cubed. Okay. Now I will do this example and then we will stop for today. So here, evaluate the triple integral. So I want to evaluate this integral. And Q is the sphere, basically, or the ball of radius 1. So x squared plus y squared plus z squared less than or equal to 1. That means we're inside the sphere of radius 1. So this is Q. So first thing then, we will determine the boundaries. So in Q, rho will go from where to where? 0 to 1. Good, thank you. Phi, the angle phi, from 0 to pi. Yes, absolutely. 0 to pi. Because remember, phi is this angle. Yeah, phi. And to cover the full sphere, you have to go from 0 to pi. And finally, theta, yeah, theta, the angle theta, and you need to cover the full sphere, so theta will go from 0 to pi. And we go now and substitute into the integral. So let me write then, what I want is to find the integral of cosine x squared plus y squared plus z squared to the power of 3 over 2 dv. So let's do it this way then. So rho from 0 to 1, phi from 0 to pi, theta from 0 to 2 pi, cosine, what is x squared plus y squared plus z squared? It's always equal to rho squared. Yeah, thank you. Yeah, it's always rho squared to the power of 3 over 2. And then the dv, yeah, remember, is rho squared sine phi, and then the d rho d phi d theta like this. So we shifted everything into these spherical coordinates. And now you can see that it's very easy to integrate. And without this change from x, y, z to the spherical coordinates, it will be impossible to calculate this integral. Impossible. No way. There is no way you can find this integral without this change of variable. Okay, so this time here and here, we can cancel. So it's going to be, yeah, let's just check this. So it's going to be, we have to be a little bit careful here. 0 to 1, 0 to pi, 0 to 2 pi. We have rho squared cosine of rho to the power of 3. Be careful, this is cosine of this, yes? And then separately, we have the rest separate. So, and then we have the sine phi, and then the d rho, d phi, d theta. Now, notice now that if you differentiate this, what do you get? Three rho squared, yeah, like that. So I will introduce 3 here, and I put 1 over 3. Because there is a rule in calculus 1, you would have seen that perhaps, is that if you want to integrate u dash cosine u, then it is sine u plus a constant. Okay. So, therefore, this integral, yeah, this integral will be 1 over 3, 0 to 2 pi, 0 to 1. Okay. And this will give you sine of rho to the power of 3, rho going from 0 to 1. And then we will have the sine phi d phi d theta, like this. Okay. Now we are going to substitute. So it's going to give us 1 over 3, 0 to pi, 0 to 1. And then we substitute. We will get sine, sorry, yes. What is it? Yeah, this is pi, yes, thank you. Yes, this of course is pi, yes. Okay, sine 1, yeah, when you substitute, and sine 0 is 0, so we're just getting sine 1 here, and then sine phi d phi. Salah, I don't know, you mean this one? Where is the rho to the power of 2 from? Okay, I'm not sure exactly what you mean. Well, what I mean, you see this rule, the way this formula is used is that, for example, if you have 3x squared cosine of x cubed, because the derivative of this is this, then this is just sine of x cubed. It's like this. So this 3 rho squared is the derivative of rho to the power of 3. So this derivative is this. So therefore, yeah. No, I did not take rho square as a common factor. Yeah, I don't. So this was a rho squared, power 3 over 2. Multiply the powers, it will give you power 3 here. And then the rho squared, I brought it here. And then this derivative is 3. So I put 3 here and 1 over 3. Anyway, you can read that again and you will see it makes sense. If you have, if you still don't understand it, I will, yeah, please do that, yes. So let me complete this. First, actually, let me just take 1 minute to take the attendance just to see who is here. Okay, let me just. Okay. All right, so let me come back to this then. Yeah. So we substitute 1, rho equal 1, so we get sine 1. When you substitute 0, it's sine 0 is 0, so that's what you get. D phi and d theta here. All right, again, this is a constant, So I can take it out of the integral. So it's going to be sine of 1 over 3. And then the integral from 0 to 2 pi. Now I will integrate this sine phi d phi. What is, yeah, that's minus cosine, yeah, minus cosine phi from 0 to pi, and the d theta stays as it is. Again, now we substitute, and this will give us 2 again, like we did before. The whole thing is going to be 2, which we can take out of the integral. Okay, so it's going to be 2 sine 1 over 3 integral from 0 to 2 pi d theta. So it's 2 sine 1 over 3. This integral, we met it many, many times. It's 2 pi. So the whole final answer, 4 pi sine of 1 over 3 is the final answer of this integral. Of course, you can find it if you want in decimal form, maybe sine 1, yeah, 4 pi, maybe 5, 6, I'm not sure. Can you try and find this number in terms of, as a decimal? Anyone? 3.5, okay. Anyone else can confirm that? Yeah, 3.5? Okay, great. So roughly 3.5. Yeah, great. Okay, that's basically this question of evaluating an integral in the sphere of radius 1. So we do it by using spherical coordinates. And I think this is where I will stop today. We are ahead of the schedule anytime. Anyway, so that's perfectly okay to stop here. Any questions at all? Anything you want to ask? Any questions? All clear? Yes, good question, Ashama. I think according to the syllabus, we have the 8th, but I've heard it, some people are saying 15th, but we have nothing official. As soon as I know officially the date, I will let you know. At the moment, we'll go with the syllabus, which says 8th of May. We have not received anything officially to change that. So for the moment, it will be the 8th of May. If there's any change, I will inform you, of course. Okay, anything else you want to ask? If not, have a great break. Enjoy your break next week. Classes during Ramadan, I think I will confirm this. It's still, yeah, it's still not very clear, but I will send you an email exactly with the time when we start and when we finish. So let me have a look again at those times, and then I will let you know. Okay? Yes, you can speak, Salah. Yes, no problem.
Doctor, I have a question in 13.5.
13.5?
Yes. I'll just say it and
Okay.
you can explain it, I will understand. Inshallah.
Okay. Can you show it to us? Or?
I don't have it now, but it was question 5.3 when you need to rearrange the integral to solve.
Okay.
He did not change it, or we solved without changing the boundaries, only the شو اسمه. dz, dy,
Oh,
and like
does it say solve by changing? Does it say solve by changing
yeah,
the order
yeah,
of
it's
integration? Okay. I will make a note of it and I will check it and send you. So what is it
no. The
exactly?
question
Which
was
question?
like why he did not change the boundary.
I don't know. I am not sure. Do you want me to have a look at that now?
It's okay.
I can open it, but let me know. What is the question? Can you just tell me the number or the example so I can have a look at it and
5.4.
5.4.
4.
And which section?
13.5.
13.5. Okay. I will check that and do you have one moment? I just want to have a quick look.
Yeah.
13.5. Okay, let me have a look. Yes. 13.5. Yes, I'm looking at it. And the example is 5.4. Oh no, if you look at the answer, I integrated first with respect to x. I changed the order. Why? If you look at the question, it starts with dz, dy, dx. Yes?
Wait, I will open it
dz,
later.
yeah, dz, I can open it actually. If you want, I can open that example now. Yeah. 5.4 starts with dz, dy, and dx. And when we solved it, we did dx and then dy, dz. So it's a completely different order. We changed the order. You can leave, by the way. It's okay. You can leave if. Are we okay with this? Salha, are you still there?
Yes, I'm here. I'm just looking at the question.
Yes, yes. Have a look if you can. I can actually, yeah.
Doctor,
Yeah, I actually just opened the file. I will show you. I will show you now. Yes, 5.4. Huh? Just, yes. Yeah, okay, let me just. Yeah, can you see the screen? Or
yeah,
can you see the question? Yeah,
yes,
you see the question was given as dz, dy, dx, yes?
yeah,
dz, dy. Look at when we solved it, we started with dx,
yes.
you see? And then we did dy and dz. So we changed completely the order of integration, yes. we did, yeah. And that was the only way we could solve this. It's actually quite a difficult question,
Yes,
I
I
have
was
to say.
confused because the boundaries changed, but now I can see that you took the boundaries first and then you solved.
Yeah, which the boundaries seem to be the same for some reason, but actually,
The other way around.
no. Yeah, it's kind of, yeah. But we first with X and then with respect to Y and Z. Okay?
Yes,
Yeah.
thank you.
Okay then. All right. Have a nice day and take care.
Have a nice spring break, Doctor.
Thank you. You too. Thanks.